Hello friends, good afternoon and welcome to EduSet Live Lectures. Dear friends, today in Computer Sciences we will be talking about Wireless Sensors Networks Part 2. To discuss this topic we have with us our subject expert Dr. Aditya Sinha. Dr. Aditya Sinha is Assistant Professor in a very prominent university in NCR of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you. Hello everyone. In this lecture we'll actually discuss about more and more on sensor networks that we started earlier. So in the second sequel we'll mainly discuss on the mathematical aspects of the advantages of sensor networks, mainly the energy and the detection advantage. Energy advantage, also known as power advantage. In this we will talk about how the sensor network is beneficial to other networks, other centralized networks, as we know that sensor network is a decentralized network. So how it is different from the centralized network? Is it beneficial with respect to the centralized networks? And if it is, then by what factor? What is the energy advantage we receive if we switch our network platform to a sensor network? Also, we'll talk about the detection advantage. Detection means what type of coverage assurance does sensor network provides, and if it provides to optimum extent, then up to what factor we get the benefit out of it. Then we'll move on to error models. Error model is a very important part of sensor network, as we know that it operates on wireless platforms. So wireless is a very vulnerable platform, vulnerable as the information in form of bits exchange can be quite erroneous over time and over distance it spans on. So we will talk about the bit error rate, that is the standard form of error. Then we'll talk about some models, the independent model and the Markov state model. Okay, then we'll discuss more about the energy conservation part, how it can be achieved with data aggregation and sleep scheduling, obviously. And obviously routing again is a very important topic. And from this lecture we'll start introducing about what the significance of routing, or what are the different deployment strategies we have, and on the basis of those strategies what type of network structure can be obtained, and accordingly the categorization of the protocols done. So the advantages of sensor network. Here the sensor network is regarded as a networked and distributed sensing environment. Why networked and distributed? It means that the sensors, the sensor nodes are all connected to each other, thereby forming a close networking platform. Networking means a node can provide its information, it can relay it towards a particular destination station. And distributed because the processing happening or any ongoing computation that is being going on over a particular node, it's nothing to do with what is the rate or what type of computations or what type of transmission or sensing, etc. Any other sensor based operations are going on. That sensor node is not concerned about its neither its nearest neighborhood or far off. So they are all apart from the centralized the administration, there is no centralized administration. So the sensors are all of their own. They are provided all the protocols with them. So on the basis of whatever the protocol, the algorithm that are fed into the sensor nodes prior to its deployment, it works accordingly. And obviously, since all these methods are energy aware, normally the administrators aim for energy aware schemes. So all these methods that are already fed into the sensor nodes, they operate accordingly in an energy efficient manner. Okay, so as we know that in a traditional approach, what happens is the sensor nodes prefer, as a sensor node prefers multi-hop communication, but in traditional system, it's not like that. It's like a one-hop transmission. Whenever some nodes have to transmit via a wireless link, what it does, it boosts up its own power level and reaches the destination, delivers the data, and then draws the coverage back to normal state. But this results in quite a loss of energy because expanding or boosting up the transmission power level is quite hampering in case of the say the energy level of the sensor nodes. So now what happens in multi-hop communication is that it normally saves transmission energy, because multi-hop, it's like not a single hop, it's multi-hop versus single hop. So in multi-hop there are a small number of hops, small distance hops, and what happens in it, that if we are using some inefficient routing schemes, then it might lead to loss of data due to long delays and heavy network congestion. Why it happens is because whenever we are routing the data in a sensor network environment, there are redundant number of nodes deployed to form a networked environment. Okay, and it might happen that the destination to which a particular source has to send its data to might be at some far off distance from its distance, means in terms of obviously the number of hops we are talking here. So as the number of hops are increasing, so the data, it keeps hopping from one node to another, still another, yet it reaches towards its destination following a particular progress direction. Right now, if during this particular process of routing, if the protocol of routing the packets is inefficient, it might result in falling our packet into loops. Like it never reaches to the destination, and it keeps on circulating between a particular set of nodes again and again. So we have to devise the routing protocol very efficiently, and obviously whenever there is a loop or any certain kind of say congestion, which may often lead to collision, of course, so it may introduce unnecessary delays. So we have to keep ourselves safe from that. So the sensor network, it supports the multi-hop communication, and this is assisted by the dense number of nodes that are networked to create an environment for information exchange. Now, this was all about energy or power synonymously, though they are not mathematically synonymous, but conceptually we can say that energy or power advantage is what we were talking about. So, and now we move on to the second very important aspect, that is apart from this multi-hop communication, what else we have in our mind is to deploy the sensor network in such a manner that we receive a proper coverage for our data. So for this calls for what? A redundant deployment of nodes in the scenario. Now this helps what? That helps to improve the SNR factor. SNR is signal to noise ratio, and this ratio, it's improved by reducing the average hops between two sensor nodes, between a pair of sensor nodes. So basically in the lecture forward, we will talk about these two aspects, the multi-hop communication part and the high sensor node density. What's the purpose of these two? And when we are discussing these two, we are mainly discussing about the say the multi-hop communication versus single hop communication, and low density deployment versus high density deployment, as high density deployment is a characteristic of the sensor network. Okay, so one is known as energy or power advantage, and the other that improves the SNR is known as the detection, that because it is connected completely to the coverage part, so we call it a detection advantage or a SNR advantage. Now, Moving to energy advantage, what is the fact that we have to establish, that we have to keep in mind before going for the mathematical proof is multi-hop sensor network provides significant energy savings over a single hop network given the same distance. Okay, so let's try to establish this. For this we take an assumption of n hop network. Now n is what? N is like the minimum number of links or hops that separates any two nodes. Now these two nodes, one of them is a source and other is destination, and within these two nodes there might be a series of so many number of nodes relaying the data from the source to destination. Okay, so since they are separated by say n hops or links, we call it a n hop network. That is, if we optimize our routing protocol in a manner, then it will not result more than n hops to deliver the data that is being raised by the sensor to be sent to a particular destination node. Now, since they are n distances apart, and earlier also we talked about this communication radius of a particular sensor node, and it is denoted by the symbol small r. So if the hops, the distance of the hop is r, and we are like the source and destination is n distances apart, then we can say that the overall transmission distance comes out to be n multiplied by r. Okay. Now the signal attenuation model then can be framed as an equation shown equation number 1, where the transmission power, the power required for transmitting a particular information in form of packet is directly proportional to the transmitted power upon the transmission or we can say the communication radius raised to power alpha. Alpha is, let me remind you, it's the path loss exponent, as we spoke about earlier also. Alpha generally ranges from 2 to 5 depending upon the type of environment the surrounding the sensor nodes, the sensor environment has. 2 means it's a free space transmission, no hindrances. And 5 means we move towards 5 if there is a dense vegetation or say the city or town environment is there with lots of buildings and malls and tall towers, etc. Okay, so in this equation 1, PR is the receiving power and PT is the transmission power. Now let's see how we can use this equation further. Now from equation 1, what we can do, we can just reframe it to get this equation 2, where PT is proportional to R to the power alpha and PR. Okay, so here the power or energy advantage of n hop communication or transmission versus a single hop one can be framed mathematically as a fraction of the single hop divided by the n hop. Okay, so since single hop, as we can see in the diagram here, that if you are following a single hop, it means that we are traversing a distance of nr. So PT, within PT we have in the bracket as specified in equation 2, it's a small r. It means it shows the distance that is important, because depending upon the distance, the transmission power has to be set. So when we are talking about the single hop transmission, we are talking about the distance nr. And when we are for n hop transmission on the multi hop part, it means that we are traversing that small distance r how many times? N times. So it's like n multiplied by PTR. Okay. So as in the example, we can see that in this particular example, n is taken to be r, value 4. Okay. So let's proceed further. Here, as in equation 3 and 4, we have just evaluated for single and multi-hop traversals, and what we can see, we plug in these values to the equation 3 that we devised earlier, and we find this equation 5, in which what happens if we put it in this particular fraction. some of the terms will cancel out and we can simplify it, and we get a term n to the power alpha minus 1. Now, what does this value signifies? It interprets that a larger n, since it's n raised to the power alpha minus 1, so if n becomes larger and larger, that is, it will support multi-hop networking in more and more way, and it will result in larger energy conservation. It will save energy in comparison to the single hop, of course. And alpha is, again, it's the path loss exponent, so it's a system defined or environment predefined factor. So all what is important is the value n. Again, we have to keep this in our mind that as a network administrator, that if n is increased, like without any bounds, we are increasing the value of n, it means that we are unnecessarily deploying large number of nodes on the same region of interest, and this might increase the maintenance and setup cost. So we have to keep a good trade-off between the cost and the benefit part. The benefit will be obviously our energy advantage. So there has to be a trade-off somewhere between the energy advantage received versus the cost, that is the input cost and whatever the maintenance cost is there. Okay. So we have established the fact that yes, multi-hop communication is better than the single hop communication, and multi-hop communication is a very crucial attribute of a sensor network. Now we move on to the detection advantage. Now, as in this figure, we can find that there's a field, sensor field with radius, the field radius is capital R, and we have to cover this field with the small sensors as in the figure below. We have some sensors with us, okay, so we have to somehow fit them into the circle so that it approximately it can cover the area. So what assumption we have here is the circular region, we have a circular region R, it has to be monitored, and the area associated is A. So each sensor node is we know that it's having a radius small r, and it's forming its own effective area of communication AS. Okay, now a very simple mathematical equation that we have here is K multiplied by AS will be approximately equal, should be approximately equal to the area that is we are given to monitor, that is the ROI, the region of interest. Okay, so if we put the values over here, the simple pi r square values, the pi being constant, it gets cancelled out, and we get a nice proportionality constant here. If you are not taking the constant, we get a proportional equation in which we can see that the communication radius of a particular node R is inversely proportional to the square root of the number of nodes that are being deployed in that particular region. So a quick interpretation that comes out from this is as the sensor density increases by a factor of k, say small k is the number of nodes that is being deployed into the region, then the communication radius also gets reduced by a factor of 1 by root k, which is a considerable decrease in the communication radius. And we know that as the communication radius decreases, it no need to cover long distances. It means that we are saving the transmission power or the communication power, right? So here with a increase in factor of k, the distance, the communication radius, that is the coverage area that a particular node is supposed to span, it gets reduced by a considerable factor 1 by root k. Now how it happens, how this sensor density can be increased? Obviously with the introduction of new nodes, And when the new nodes comes into the scenario, it minimizes not only the distance of the transmission, that is between the intended source to the relay node or the intended source to the destination part, it also creates several alternative routes for transferring the message. Say for example, if a primary path that is being currently taken goes down, it fails or it gets congested, or the collision probability associated with that path is very high, or any other reason, that primary path can be dropped and we can take several secondary or ternary paths, the backup paths we can say, so as to increase the reliability of information transmission in a sensor network. So as this average distance reduces, what happens? The signal has to travel less distance, and since signal is traveling less distance, it will tend to bear less amount of noise or distortion in it, and that is what we are targeting for. We have to improve SNR and decrease the noise level so as to improve the information quality. In the figure we can see some examples. In this T and R, the transmitter and the receiver, new nodes are introduced, and as we can see that as the cross marks are showing the new nodes here, and it means what? Between two dots a new node is getting introduced, so the information is now not traveling between the dots, but there is this cross mark, this new node introduced, so the distance visibly it gets reduced. Okay, and also in the other diagram we can see that there are many alternative paths to reach from S, the source, to destination via A or via B, apart from the primary path, that's the boldened path. Now further, now let us consider, this was just a quick interpretation that we have made. Now so far we know that yes, there is some scope of improvement towards this improving the SNR, but exactly by what factor? We are also interested, since we are dealing with a mathematical proof here, so we are also interested about by what factor this sensor network characteristic is beneficial for us as network administrators. So let's consider here the acoustic sensor devices. Okay, so here they are operating say in a 2D plane. Acoustic sensors are a type of sensors we have already discussed that they operate with sound energy, okay, rather than radio energy. So we take a different type of sensor here just to experiment with, and here the communication distance is R, because that's the communication coverage, communication radius, so the distance is R, and according to the free space path loss model, what we have is PR proportional to PT by R alpha, and if we take alpha here too, considering a free space obviously, so it happens to be PR proportional to PT by R square. Now if we try to find out the SNR is what? The PR by P noise, it's this factor that is defined as, and since it's in decibels, so whatever any term that any value we want to turn into decibel, what we do 10 log 10 and that value, right? So the same thing we have done in equation 8 and 9. It's 10 log 10, the base is 10 unless otherwise mentioned, and it's a fraction of PR by P noise. Okay, so we get a nice looking equation as in equation 8, and for 9 what happens, since we know that we are increasing the density by a factor of k, so it's the improvement is like the the communication radius, the communication, it's going down by, it's getting decreased by a factor of 1 by root k. So the SNR will be now SNR divided by root k, because it's getting decreased by this factor, right? So now with this new distance we can compute the SNR, the same formula, and we get a different output as shown in equation 9. Now to find out the advantage, the SNR advantage, what we do, we subtract equation 9 minus 8, okay, and we find that it is 10 log k. The interpretation behind this is that since log k is written as 10 log of log k, because it will come into decibels, but the factor that we are interested over here is log k. An increase in sensor density by log k will ultimately improve the SNR at a particular sensor node by the factor log k. So, this is a considerable, is a good advantage, good benefit that we are getting in terms of detection, there is the coverage or SNR benefit also. So, all at the end we can say that in terms of energy as well as coverage, the sensor network that was claimed to be beneficial is actually, it is like that as mathematically proven. Thank you. Welcome back, viewers. Now we'll study about the error models in sensor network. Now errors are what? They are very dynamic when we talk about the wireless, when we take up wireless as the domain. So what happens? It's having different pattern. The pattern of error occurring is very dynamic. It may be stable at times, it may be bursty some other time. And the quantity, the amount of error that happens instantaneously is also very different periodically. So there is very difficult to establish a pattern in the error so as to take up some additional measures to deal with the errors in wireless environment. So let's try to understand more on it. The factors that affects the error, that is, or we can say that the factors that helps in understanding or that contributes to error in transmission, what are these factors are? The first is physical media, the wireless, it's always vulnerable to different types of distortions in the signal and creating noise, adding some like erroneous elements to the ongoing communication, etc. So the physical environment, the physical media inherently is vulnerable to all these error factors. The second is node speed and velocity. Now as the node, or if the node say is mobile, if say for example the clusters are formed and the cluster heads are actuation units, or better known as actuators, the nodes with mobility. So if these nodes happen to be mobile, mostly found in applications like vehicular communications, where the vehicles transmit the information even when they are mobile, they are moving from one area to another, right? So what happens in that case when you are moving from the coverage area of a particular network administrator to some other network, there is a very high chance that the resources that get switched from one network to another, there can be gaps in them, there can be miscommunication, and as a result of which what happens, the resources might not get engaged in time, thereby leading to certain losses in information exchange, or this information can be in form of video, voice calls, or etc. So the node speed and velocity, in which the rate at which the node is being traveling, is also important. It also contributes a lot in determining, or say predetermining the error in transmission. Because once we have a predetermination of yes, the error can be happening, or it can be in this particular pattern, if we are having a prior knowledge of this, then as administrators, certain checks can be put on the this thing, so that error handling and error correcting mechanisms can be introduced. Okay, and the next is topological obstructions. Yes, topological obstructions means the impediments like the signal that is being traveling, it might get obstructed, it might get splitted or refracted, it can get refracted from its path, and this will happen. Why? Because the tall buildings and towers, the different nature of the surrounding, etc. So, this also is one very important factor. Apart from that is multipath routes, say information, since we know that the information exchange is on wireless, so it's not very reliable. So, just to have backup of the data that is being transmitted, often the routing protocols have a backup path associated with it. There can be one or there can be multiple paths depending upon the nature of the protocol devised. So, what happens when the information reaches from the source to destination following these multiple paths, there can be different versions of the same copy of transmitted data received at the other end, which if not resolved, if the destination station is not having proper error correcting codes or assembling strategies of the deassembled packets, because we know that the packets being transmitted are often deassembled into small frames. So, the destination station should be equipped in such a manner that they should have a good assembling, packet reassembling and assembling strategies with them, because if they are not there, then it becomes very difficult to find out which of the, say, some n versions of the same copy of the transmitted data received is correct. So, and then also the channel fading, the different associated problems with the physical layer, interference, etc. They also contribute to the noise or the error factor in wireless transmission. Now, a very good survey has shown that the fiber optic based channels, in this what happens, the errors that are considered to occur randomly with very low rates. The error occurring rate is very low in case if it's a wired communication, we get it in the order of 10 to the power minus 9 or even better. So, when we are going for wired communication, we are hardly concerned about the type of error that can happen. Obviously, there are security issues and hacking and all those things, they are there, but inherently the error rate is very low. But what happens when we come to the wireless domain? In this, the bit error rate is like 10 to the power minus 6 or even worse. It comes towards like 10 to the power minus 5, 4, like this, and also they occur in bursts. So, the rate is undefined and the errors are often bursty in nature. So, let us now study about what a BER is. It is an important parameter, it is synonym to bit error rate. Here what happens, it is mathematically defined as the fraction of number of bits received with error at the destination end, obviously, divided by the total number of bits that were actually transmitted by the source. Now, this mathematical equation that is given in equation 11, this is actually the signal bit error rate. We have another, there is another term, there is another very important term which is known as information bit error rate, and in this what happens, it is a fraction as shown in equation 12, is it is a fraction of incorrect bits after decoding at the destination divided by the total number of bits correctly decoded. So, this is a different parameter, different issue that is to be dealt with the destination end, and nothing to do with the signal BER. So, in this study, in this lecture, we are concerned about the signal BER, and that is the bit error rate that tends to vary, or its pattern is very difficult to recognize as in case the wireless characteristics are. So, we are more and more concerned about the signal bit error rate rather than the information bit error rate. Okay, so because bit error rate is something that can be corrected by the correction mechanisms and other associated assembling and deassembling mechanics at the destination part. Okay, now the bit error rate if we take up an example, say out of 10 to the power 5 bits that are being transmitted, out of them say 9 bits were found to be corrupted. And if this is the statement, we can say that the bit error rate is like 9 into 10 to the power minus 5. This is how we state the bit error rate. And it gets affected by the channel noise, yes, the interference, in what way the signal is getting distortion. So signal distortion is also one important factor that plays an eminent role here, and the bit synchronization, that whichever bit has to receive earlier, or it has a special significance to be received earlier, is coming or it's getting delayed by a considerable amount of time. And what happens in wireless, that there is always a time window, that if within this time window the internet information is being reached, then it's okay, fine, it will be taken upon, otherwise it's simply discarded. So things like this should be taken care of. So and if you're talking about the error models here, now since we know that what are the different factors that affects it, so the models that are there abiding these factors are the independent error model and the two-state Markov error model. Independent error model is a very predominant one because of its simplicity and ease in implementation or understanding. It's very much practically used in various domain. So what happens that the main drawback that it has, it's a memoryless model. Memoryless model means that there is no temporal correlation between the symbols getting corrupted over time. But what we were focused earlier as administrators is that if we have to establish some kind of pattern, so that with the help of mathematics, with the help of probabilistic study, we can prior to this communication, we can find out that what is the chance of getting our information corrupted, right? So this method, this particular model is not a very accurate one to take upon, as if we follow this model, then the errors are actually occurring at random and they are independently occurring. That is, they have no relation in their occurrences with respect to the intervals, in between intervals. Okay, and if we frame it mathematically, then it's given by equation 13. Now, how this particular thing comes, that the packet error probability is almost equal to PE. PE is what? PE is our bit error rate. So it's a product of bit error rate and L, that is the size of the L bits being transferred. So there's the size of the small frames, that is, a packet is subdivided into frames and each frame is like L bits, so like that. So how it comes, it's actually in this manner it's calculated. PE is the bit error rate, and since the packet is broken into so many segments, if one of it gets into error, it means that the whole packet is in error. Okay, so if let's see it in this manner, that PE is that our packet is in error. 1 minus PE, it's not in error. Okay, and to the power L, it means that L means all the frames that we are taking into consideration. Okay, so this probability is giving you the idea that at least one of the sub segment or that of the packet, that is the packet is broken into segments, if one of them is in error, what is the probability of that? Because if we can get a probability of that, we can obviously find out that what are the chances of getting the entire packet to be corrupted. Now let's see the second one, the two-state Markov error model. In this, what happens, we go by the convention that yes, error occurs in bursts and they has to be corrected, but their this trend is very difficult to detect, etc. But what we can with this model, what we can do is we can define two states, a good and a bad state. Now, what is a good state, or the state that is defined by this goodness is known as the good BER, the good bit error rate. Though there is some kind of error, but somehow it's good. It's stable, it's not much in quantity, so it's a good bit error rate, and counterpart, there is a bad bit error rate. Good bit error rate is acceptable, it's recoverable, and they are small in number. In contrary, bad error rate means they are very large in number, which is like very unacceptable, and it cannot be recoverable, right? So as in the diagram, we can see that the bad sectors, they are showing quite lots of errors, and they are coming in bursts, and their pattern is very difficult to identify. But in the good part, there might be no error at all, or there are very few. Obviously, some threshold can be set to allowing some particular bit rate, that if the bit rate is this much, maybe less than some value alpha, then we can regard it those in good bit error rate sector. Okay. So in this way, we can define into states of good and bad, and with the help of Markov process, we will try to establish what type of performance this error model can provide us. Now here in the diagram, it shows that there's two states, and there are transitions between these two states. Each transition is associated with a particular probability. There are 4 probabilities with 4 transitions. And since there are transitions, we have a transition matrix with us as in equation 14, and we have also we can see that there is a example also that has been taken up here. Say 0.6 means that the probability, if we are getting a transmission that belongs to that is associated with good bit error rate, will keep on getting it for with a probability of 60%. So if we are in state G, then it's a 60% chance that we will be in G for the next obviously time instant. Okay, everything here is for the next time instant. Given in this time instant we are in state G, next instant we will also be in G. What is the probability for that? It's a 60% chance, and the rest of the 40% we can receive like bad bit error rate with us. Okay, so again, if we are already in the bad state, then what is the probability that we will get a bad packet, or a packet that is hampered with bad bit error rate is TBB, right? This is the probability associated with it. So it can be the according to what the transition matrix we have, the example can be mapped. Okay, and what else we have apart from the transition matrix is the initial state distribution matrix. Apart from the transition factor, that if given the state and what is the probability that will jump into some other states, this probability, along with this probability, we also need what is the initial state distribution matrix. That is when the communication starts, what are the chances that it will start being in the good state, or it will start being in the bad state. So that is known as initial state distribution matrix, and we have values here as pi g and pi b. In example, say if we have no idea of how the communication will behave, we can take it as a 50-50 chances. So we have taken over here as a pi 0 or pi t equal to 0 as 0.5, 0.5. Now it depends upon the network designers to observe what is, depending upon the past experience or the past communication that has been there, that what are the chances of initial chances of getting a packet with good error rate or a bad bit error rate, and accordingly the initial distribution matrix can be set. Here in the example it has been taken as 0.5, 0.5. And now how to find out the probability of getting into bad or good state for the next time instant? It is like pi k, that is for time k. It can be defined as a product of pi k minus 1, that is one step prior, multiplied by the transition matrix. The transition matrix has to be calculated once and it remains same, right? So for T1, if we are calculating pi 1, it will be pi 0 multiplied by pi 0 multiplied by t. Again, we are calculating for pi 2, it will be pi 1 multiplied by t. So we go on doing this calculation till we get some value pi k that on the course of iteration becomes equal to pi k plus 1. That is, we keep on doing our iterations again and again, and we end up with a constant value which repeats itself due to matrix properties, etc. So this is regarded as the steady state, and this k will be the steady state part, and the value that we receive here it's like constant. It will not change further, and it's regarded as pi star. Now when we have this value pi star, what we can do ahead is we can obviously find out the actual bit error rate. Remember, previously the bit error rate was simply the whatever the designers after the communication they get, that okay, after this communication this particular bit error rate is there, because it's only the after the communication in independent model that a designer or the person at the destination side can get to know that okay, these many bits were transmitted, and out of this I am getting some say 9 or 10 bits into error, so the bit error rate is this. But here what we are doing is we are calculating the bit error rate in advance, given certain probabilities on the basis of prior transmissions or prior experience of that particular channel, on the nature of environment or the transmitters and receivers, the sensors, etc. When we have the probabilities, we can have this good BER and bad BER, and then pi g and pi b can be calculated, as we have just now we have seen pi star, how pi star is being calculated. Now this pi star can be pi star g and pi star b. Okay, so once we have all these values with us, we can deduce the bit error rate. Okay, so this bit error rate will help us to determine that to what extent the transmission will be bursty and how it can be amended. Now we'll move to the energy conservation part. As so far we know that why energy saving is very important. It's solely because of this reason that the sensor nodes are battery operated. So everything, every processing capability, they are all restricted to some extent. Okay, so simply speaking, the two very important strategies that are being used for conserving the energy is data aggregation and sleep scheduling. Data aggregation is what? It's a data oriented approach. Okay, it combines the multiple packets or multiple sensed data, there's the data sensed over multiple intervals into a single packet. Okay, so and what happens from this, that the number of transmissions are being reduced, because now instead of sending all the packets as transmission, every time it gets a new packet it will send it, so with aggregation what happens, we are summarizing the values into one packet and then it's being sent. So obviously the number of transmissions are getting reduced drastically, and it will certainly depend upon the temporal and spatial similarity that inherently exists between the data sensed by the sensors in close proximity. And second, we have sleep scheduling strategy as well. This is topological based approach. Data aggregation being a data oriented approach, nothing to do with how the sensor nodes are laid out on the region of interest. But here, when sleep scheduling is concerned, the topology is very important. It restricts certain nodes to transmit the packets. It may be zone wise, or a particular zone where the demand of data or the the query is not flooded more often by the base stations to gather data, say for example. Then in such cases, we can temporarily attempts can be taken to turn off the radio of the sensors, so that they do not waste their energy in overhearing other transmissions, other ongoing transmissions in the nearby area. So mostly what happens, transmission from a group of nodes are restricted, and it certainly depends upon only the spatial distribution of the nodes first, and the second is the node functions. Whether if say for example, if a node is functioning as a member node of a cluster, and it's also vested with how to manage or coordinate the sensors within that particular cluster. Say for example, it's a cluster head, or it's having some actuation capabilities, etc. So in that case, its transmission cannot be compromised, so we cannot put that particular node to sleep. So the node functions are important, the duty cycles are important, apart from the spatial topology distribution of the nodes. So let's see now what data aggregation actually is. There are two types of data aggregation, lossy and lossless aggregation. Depending upon the type of application, whether it can tolerate some data to get lost, then it's fine. We call it a lossy aggregation. In lossy aggregation, obviously the transmissions will get decreased to beyond certain limit, and there can be like considerable increase in energy, overall energy saving. And if it's a lossless aggregation, it means that it cannot bear, the application that we are dealing with cannot bear losses in aggregation in the computation part. So more and more data has to be taken, so there can be a little increase in transmission energy as the number of transmissions tend to increase. Okay. And what are the ultimate goals we have is it will certainly minimize the number of transmissions. Obviously aggregation is doing that, and it will reduce the bandwidth usage, and ultimately the unnecessary energy consumption in transmission as well as reception can be reduced to a great extent. Now before doing aggregation, we need to collect the data. Now what are the different ways that data collection can be done? It can be done in a centralized manner or in a clustered way. So what happens in a centralized collection is that all the nodes are supposed to send their data to base station, and since all the data are being sent, so it calls for a redundant transmission, leading to network congestion, which is very likely to happen, huge energy drainage not only for a particular sensor node but also of the entire network. In clustered collection, now the clusters are there in the domain, so what happens, the nodes are not sending the data directly to the base station, but they are sending it to the base station and to the cluster head, that is the in charge of cluster. Now this actuators, often these cluster heads are like actuators, so these actuators, they are in charge of delivering their data to the base station. So obviously fewer transmissions, so energy conservation is more. Now once data is collected and aggregation is done, what are the important factors we have to keep in mind, the trade-offs? They are energy, because the computational energy should not be much that it crosses over the communicational complexity. So the type of computation that is being involved in data aggregation should be minimized. The second is latency. Latency is what it's in network aggregation, it mostly happens because in network aggregation, the parent nodes, they often wait for their child nodes or leaf nodes to report their data, so that they can collaborate their data along with the parent's own data, and then they mine up the final information before sending it to the base station or the root level station. And then of course accuracy is important. Since data is suppressed, we have to keep track of how much data is being lost or suppressed, so that the data coverage is not hampered. And obviously fault tolerancy is again important, owing to the unreliable nature of wireless, and security is another additional feature that should be taken upon. So all these trade-offs are conflicting with each other. as we can see that since it's wireless, so error occurrence is very high. So often the communication is over multiple paths. Multiple paths, it means multi hops are going to be taken. As a result, there will be data duplicacy and routing overheads. When there is data duplicacy, it violates the initial motivation behind the data aggregation, because data aggregation says there will be no data redundancy or duplicacy and everything is summarized into one. But again, owing to the wireless nature, what we are doing, we are replicating the copies of that same data and we're transmitting through different paths. Okay, so it's violating, it's contradicting with the initial motivation behind data aggregation. So these are the trade-offs that has to be balanced according to the application need. If, say for example, the application is such that it requires energy to be optimized, then the others latency, accuracy, fault tolerance has to be taken at some minimized levels, or vice versa, whatever the application demands. In security, we have two levels: authentication and encryption. Okay, authentication is like who are the intended person at the end user level who can access the data. So it's all about access control. And encryption is since the message is coming through wireless domain, then what type of encryption technology should be there so that the impact of noise and signal distortion is less and less, or it's such that it can be, at least it can be recoverable. Okay, so these are the two impacts, and the complexity increases obviously as the level of data aggregation tends to increase. Now let's come to routing. As routing, for routing, it is very important that what type of deployment, initial deployment of node is. It can be a manual deployment or it can be a random deployment. If the manual deployment, it means that we know the locations and data can be routed through predetermined paths, right? And if it's a random deployment, the sensors are stochastically distributed. We are not knowing that where these sensor nodes are getting localized. So here optimal clustering is required, multi-hop, efficient multi-hop routing, etc. should be taken into consideration. So we'll study more on this in the next session. Thank you.
On that note, I would like to thank ma'am for this very enriching discussion, and thank you dear friends for watching our show. Stay tuned and keep watching. Thank you.